Okay, we see the proof first. Let's fix up our notation, okay, so that we don't get confused. P and D we already know. Let's say X star and Y star are the optimal solutions for dual respectively. Correct? Okay. And what we want to show is that if no technicalities happen. Right? And you remember technicalities is one is infeasible, both are infeasible and things like that. So if none of that strange, weird things are happening, both are feasible, then this is the case. Okay. Before I move forward, I wanted to just, as an aside, I want to mention convex programming. What do I want to mention about it? Notice that many of these things which we are saying about linear programming, the niceness comes because the feasible set is a convex set, right? So there are cases, there is this bigger branch which contains linear programming and many other places where my feasible set is convex and then I want to optimize some nice function. It could be a quadratic function, it could be a linear function, it could be a convex function, so on and so forth. But the idea is that still some of the properties of linear programming can still be used here, and people in optimization actually study convex programming. I remember a case when I went to this optimization person, told my program, he said, oh, it's not convex, we can't do anything. So that's generally the feeling they have. Convex, good, not convex, not good for optimization, right? So this is a major field of study of which LP is a very, very small subset. There is another small subset which kind of comes in between which is called semi-definite programming, and I will cover that because that's also used a lot in complexity theory, semi-definite programming, and this is where my research started, so kind of fond of it. So I will tell you about this whether you like it or not. But yeah, so LP, semi-definite programs, convex programming, and what you realize is that this is the strongest. That means very few programs can be written like this, very few in the scheme of still a lot, but few compared to others, though it has strong properties. As you move this side, the set increases, but then the properties decrease. Duality is one thing which works out for convex programming. You can define what we call dual of convex cones. So instead of this, we can say X is part of some convex cone, and then the dual will be all the things which have positive inner product with everything here, right? Why were we saying X should be positive? Because X positive is the elements which will always give you positive when multiplied by something which is positive. Okay, similarly you can define this idea of dual cones, and this entire duality theory can be extended to convex programming. But then strong duality does not come for free. Weak duality, duality theory works out. Strong duality, you have to be careful. Here it is automatic, here it is almost automatic, here you have to work for it. Okay, so in the big scheme of things, it's nice to remember, yes, LP is something we are studying, but there is a bigger class of problems. So if your problem is not LP, not all hope is lost. Probably it is semi-definite programming, then you are still very, very okay. If it is convex programming, you are fine. If it is not convex programming, change your problem. do PhD on something else. No, I'm just joking. There are other techniques too, but this is the general idea. Okay, great. So one of the nice property of LP is that strong duality almost always holds. And if we have this convention of minus infinity and plus infinity, then it's kind of always there, right? Okay, now we are ready for the proof. I will erase this, you will remember this. Actually, let me just keep it, I think it's important. So let's take the first case. Suppose P is empty. Okay? What does this mean? That we have to prove. That's not. Now we are in the. Okay, wait. Proof. Right? So we can't say that means this is infeasible. That is what we want to prove, right? So now, but from beforehand, before knowing the statement of strong duality, if someone tells you this, what do we know? There is no x greater than or equal to 0 such that Ax is equal to B. That means I'm not looking for English equivalence. I'm looking for a mathematical equivalence. You should be able to tell me this. I told you strong duality realizes on what? You're going to elementary. Before that, there was an elementary version of duality. Yes. So what does it mean? B is not in the cone of vectors of A. Ax is equal to B, x greater than or equal to 0. This is saying that B is not present in the cone, finite convex cone generated by the columns of A. Right? So then, what does Farkash lemma tell us? There has to be a hyperplane separation. There exists a y such that, which sign do I prefer? Okay. Okay, in the original thing, if I had written the opposite signs, don't worry, you can multiply y by -1, right? So there is a hyperplane separating the cone and the point P, right? This was the hyperplane separation theorem. Great. Now, D could be empty or D could be non-empty, right? If D is empty, there is nothing to prove. Both of them are empty, we never said anything. But suppose D is non-empty. That means there exists a y prime such that A transpose y prime is greater than or equal to C. Right? So, what should I do now? Now I'm not viewing this as a cone. I'm viewing this as a constraint here. And what is my task? I want to prove that this is, what do I want to prove? P is empty. Dual is feasible. So I want to prove that this is unbounded, right? So you look at these equations and tell me why it is unbounded. You should be able to see this. Exactly. If I take y prime, add multiples of y, what happens? Is this constraint violated? It cannot be, right? So look at this solutions. Right? They are all dual feasible. Everyone agrees? This is also dual feasible because A transpose y prime is greater than C, A transpose y is greater than or equal to 0. So A transpose Zi is also greater than or equal to C. You take a positive quantity bigger than C, you add a positive thing, it will still remain bigger than C. Again, this is vector inequalities, by the way, right? But it is fine. But what is happening to the objective value? B transpose Zi is B transpose Yi plus, B transpose Y. This is a fixed quantity. B transpose Y is negative. As I tends to infinity, this becomes minus infinity. Okay, right? Because I have constructed feasible solutions of dual which are taking my value to minus infinity. So that means dual is unbounded. Okay, clear? And by the way, if dual is unbounded, then clearly primal is infeasible. Right? Why? If dual is unbounded and if there is a feasibility, then there I have a lower bound. But I know lower bound cannot happen because this is unbounded. Right? So this unbounded feasibility, all that we can now leave. And we know dual of dual is primal. So we can say that if you know P is no, D is empty, then dual is unbounded, or right? So we leave out everything now. We are in the final interesting case, which is P and D are non-empty. Okay, so both of them are non-empty. Now I want to prove that both the values agree. I get this. This is my target. This is the interesting part of the proof. Okay, technicality is over. This is the main part. So let's focus. And again, the idea is to apply Farkash lemma, right? But what to apply Farkash lemma on? Right? I don't see any like Ax equal to B is feasible. A transpose Y greater than equal to C is feasible, right? So there is no cone infeasibility here on which to apply Farkash lemma. But let's say, so are non-empty and both are bounded. I can assume that because if any of them are unbounded, then I know that other has to be empty, right? So if these are non-empty implies both are bounded. So now, suppose the optimal value of primal is P star, dual is D star. Okay, this is just notation. And this is equal to C transpose X star, B transpose Y star. Okay, and I want to prove that these are equal. So now the infeasibility or the fact that I can't write something as a cone is that let's look at everything in one more dimension. And this is probably something which I mentioned. This is going to be Farkash lemma, or this is going to be hyperplane separation in just one more dimension. Now let's look at all these points. Okay, this such that x greater than or equal to 0, right? What do I know about this? If Ax is equal to B, right, then C transpose X is less than equal to P star. That is the optimal. Right? So what do I know? If Ax equal to B, then C transpose X is less than equal to P star. Other way to say it is, can you find a point which is not part of this? Not in terms of X. Okay, very good. B comma P star plus 1. Right? This is not part of this. Agreed? Though, this is a good question if you have done a discrete structures course in previous semester. But if you are looking at linear programming, you don't want 1 here. You want epsilon. Epsilon greater than equal to 0. Right? Why 1? This is a continuous domain, so we want to say that any B comma P star plus 0.0001, B plus, comma P star plus 0.00001 is not there in this code. Okay, and now if I show solution for any of the epsilon here, then I am done. Okay, so this is the plan. Once I know that this point does not exist here, I can apply Farkash lemma. And using that, I will construct a solution for the domain. So let me just write down the idea. So yes, when you look at it, see here it was quite clear how this was hyperplane separation question. What you have to realize is that you can actually write your objective function also as a constraint. You can write or is this feasible? Right? So you can apply, you can look at this in Vermoon dimension and apply Farkash lemma. Okay, but let's not worry about this. Let's see the straight direct proof. We are just going to apply, we are going to look at this cone. Okay. Now, ideally there should be vectors here, but it is understood. This is a matrix. I am talking about the columns of this. So, columns of A and C, they generate a finite convex cone, right? And we also know this is the point outside the cone. Okay. So, idea, so one way to kind of understand it is my y-axis is going to be this last axis. Okay, so I have this region. This is my feasible region. Okay, not feasible region, but x greater than equal to 0. What do I get here? Right? Now, this is the line where, let's say, this line represents B. Okay, and this is taking different values at the last coordinate. Okay, so this is in some sense B comma infinity. This is B comma 10 to the 10 or whatever. You know, and this is P star. So I have rotated my feasible set so that I am aligned with this axis, right? And here the feasible region is going to be this line, but that doesn't matter. What I am going to say now is that if you look at, so I don't know, probably 10 to the 10 is here, I don't know, so I don't want to write 10 to the 10, but be a comma, very, very large value. But, so now, if I look at this point is going to be outside the feasible region. And if that was the case, there would be a hyperplane separating it. But that hyperplane separation will give me a dual solution. So that's why there cannot be any gap between it. All the feasible solutions of dual were giving me upper bounds, but if the upper bounds were not tight, then there is a gap here. But the gap allows me to give a better upper bound. That's the idea. Okay, so let's apply Farkash lemma. Since you guys are sleeping, you will apply Farkash lemma. I will not. Wake up. What does Farkash lemma says? There exists a y such that, or there exists a y prime such that let me just see if this is the sign I want, or I want to, okay, yeah, this is fine with me, okay. And obviously if you want to reverse the sign, you can multiply by minus, but there is a y prime like this. And now obviously one of this coordinate is special, right? So I would split it with this special coordinate. So let's assume y prime is y comma u. Sorry? Oh, y is any general, I'm just writing the name. I'm calling the first m coordinates of y prime as y, the last coordinate as u. Yes. You can check that. It's just matrix multiplication, and you can check that. And I'm going to write it for you. This is going to say that A transpose y plus and why didn't I apply a transpose here? It's a number. U is a number. Remember, this is one-dimensional multiplication. P star plus epsilon is a number. This is a matrix. This is a vector inequality. This is a number. Okay. Oh, sorry. This is also, finally, this is a number. A transpose y plus C transpose. No. Sorry. This is a vector inequality. This is a number inequality, right? Because B is a vector. U is not. Right? Okay, good. Where is the eraser? Yeah. And now, obviously, just to make things simple, now even if I multiply y by any scalar, right? Still, these inequalities will remain true by a positive scalar, right? So that means I can assume that my u is equal to, is that okay? Sorry? Very good. It's okay? Yes. Right? So since I can multiply u by any scale, or actually I multiply all these equations by any scalar constant, that means I can make sure that my u is either 1 or -1 or 0. Does that trouble you? Right? You have some number. It will either be a positive number, then you can reduce it to 1. It's a negative number, you can reduce it to -1. If it is neither negative nor positive, then the only possibility is 0. Hurrah, you don't need to multiply it by anything. Right? So you can restrict it to this case. And why I'm looking at this case is, remember, if u is equal to 1, right? Sorry, I probably want to switch these. Yeah. So u equal to 1 or u equal to -1, this starts giving me dual feasibility. Oh, I'm just simplifying my analysis. By saying that, so now I'm instead of saying that u is some any number and then keep dividing by it, ultimately what do I want? I want a dual feasible solution, right? So you see that this is a dual feasible solution of that form with u extra. This is almost A transpose Y kind of greater than equal to C, right? So if the things are right, you would be good. Okay? By the way, there is no transpose needed here. U is a number. Okay? Yeah, so probably it's the column of A transpose I was talking about. One of this, but those will match. I don't want to do the hard work, but basically, yeah, so you have to just see whether this implies this is the cone generated by the rows of A or the columns of A. That you have to see. Or, yeah, it is C transpose or whatever, so you have to see. Okay, but this will match, like this is not, it has to kind of one more dimension, so. Okay, great. So the meat of the problem is here. How do I use these to give me a dual feasible solution? Okay? Okay, good. So let's say u is equal to -1. Okay? Then I get that A transpose Y is less than equal to C. Okay? Sorry? C is a vector. This is a vector inequality. Okay? So probably it is C transpose, but again, you have to match the dimensions. Right? So A transpose Y is less than equal to C, but from here, B transpose Y is greater than P star plus epsilon. Correct? Okay? This is dual feasibility, but in the opposite direction. And you remember our meta thing? The meta equations which we had written? If the dual feasibility in the opposite side, then we should not get upper bound, we should get lower bound. But this is giving an upper bound. There is some issue. So this is going to give us a contradiction. Okay? So we just take this multiplied by x star correct? What is this? What is this? X star is a feasible solution. Right? These are basically I have applied the meta inequality here. Right? So in some sense this is saying that your picture will be oriented in the correct way. Okay, I'm just giving you intuition, but it is basically saying that u is equal to -1 is not possible. So it is basically saying that this thing can't go in this way. That is a contradiction. Okay, so final thing has to go up. That's the kind of that's what this all calculation intuitively is saying. Okay, good. So case 1, case 2, u equal to 0. You will tell me what happens at u equal to 0. Do it on your paper. Pen and paper. Why? Case u equal to 0. Do you get a dual feasible solution? You have these equations. I'll just put u equal to 0 here. Then but we have already assumed that primal was feasible, right? So u equal to 0 is also not possible. Okay, again intuitively this means that this has to be a non-trivial picture in this dimension. Okay, what does u equal to 0 mean? U equal to 0 mean that this hyperplane, it has nothing in this dimension. So it is in this, the picture in this dimension is kind of trivial, it is inside that. So all those weird things are not happening. So these are again cases which we are ruling out by saying that, oh, this picture actually looks like this, everything is feasible, then I'm going to have some meat here. It's not like these are squished inside n-1 dimension subspace or something. None of that is going to happen. Okay, what should I erase? I can erase this. So if u is equal to 1, A transpose y is less than equal to C? Huh? Minus C. Good, thank you. And u is 1. Okay. What do I want to do? I want to create a feasible solution of the dual. Looking at this equation, how do I create a feasible solution? Replace y by minus 1. And I can play this game for okay. So that means this implies d star is less than and now there might be people who are very familiar with analysis and you might ask, oh, what if infimum, supremum and all those things? Look at the note. There is an extra reading. It basically says we are in the nice world with this linear optimization and everything. we know that the sequences will converge. So we are okay. We don't need to, in linear programming, we'll never talk about infimum, supremum. We always talk about min, max. What is the first property of duality? Any feasible solution will always give you a value higher than P star. Proving strong duality, never forget weak duality. Right? So we know that D is definitely going to be bigger than P star. The question is it equal? Okay, so this line is just for Dev. Okay.